So we're going to finish off the material in this last week's stuff that I'll do over a couple of videos. We're going to be looking at when to start with when two projective points are in the same line. Now, projective points are fundamentally lines in affine space of one dimension higher. So when are two lines in affine dimension space, well, what do they span? They span plane. And in fact, any line within the same plane is going to end up giving us the idea of collinear, so points in the same line in projective space. So we should be able to detect that at the level of affine coordinates, and so that's going to be more or less the first remark. So section 5.3, collinearity. So recall that if we are looking at the third affine, so in the third affine chart of P2, so P2 of course are given by the homogeneous coordinates x, y, z. So this is where z is not equal to 0. We divide by z to get the affine chart. So uv, which are in a squared, where u is x over z and y, and v is y over z. Okay, so what does a general line look like in affine space? A general line in A2 is just given by one equation, one linear equation. We are using AU plus BB plus C is 0. And if we were to put back the these fractions x over z and y over z and multiply it by z, we would get that this is going to happen if and only if AU plus AX plus BY plus CZ is 0, which is the equation of a plane. So a plane in A3, and generally speaking that is going to be what we'll get, two-dimensional plane, not a hyperplane, a two-dimensional plane in a n plus 1. What we get in general, we get that a line in Pn is a two-dimensional plane through the origin in a n plus 1. So let's just give that definition formally. We say that 3 points, so 3 projective points, x1, x2 up to xn plus 1, y up to yn plus 1, z1 up to zn plus 1 in let Pn are collinear, two L's, are collinear if there is a plane through the origin in an plus 1 which contains all of the lines defined by these points. So I could put, if I like, I'll put r times, because we're always working with real numbers, r times x1 up to x n plus 1, etc. So there's a nice way to be able to work out if you have three collinear points in P2. So this amounts to saying that there are three lines in A3 that are all in the same plane. Well, if you had such a situation, and the vectors that generate those three things aren't giving you any volume, right? Because they're flat in some plane, and so you can detect it through the determinant. So so in P2 we can use the determinant. The three vectors defining lines in A3 are contained in a plane if they subtend, if you like, no volume. So, i.e., we can just calculate the determinant of x1, x2, x3, y1, y2, y3, z1, z2, z3 equals 0 if and only if, I'll just write x underline, y underline, z underline are collinear. So let's do an example. So example 516. Consider the points A, which is equal to 0, -1, 2. B is -1, 0, 3. C is 2, -4, 2. So let's see if we can work out whether they're collinear. So one way to do this is to get ourselves into an affine chart and then check if these points are on the same line. Another way to do that, another way to do it is just to take the determinant. So I'll do both ways round. So are they collinear? So in the affine chart, A23, so I've chosen A23 because I know all of these final coordinates here are non-zero, so I can divide by them. So in that case, A is equal to 0 minus a half, just dividing by this last one. B is equal to minus a third, 0. C is equal to 1 minus 2. Then I have to decide whether these are all on the same line. Well, they will be if the difference between the points, between the points A and B and A and C, that those are the same, those are vectors which are multiples of each other. So if I put AB, that would be the vector minus a third, a half. AC would be the vector so I'm going to go 1 and then minus 2 plus a half, which is minus 3 over 2. And indeed, if I multiply AB by 3, let's say by minus 3, then I do get AC. So these are collinear. And if you didn't believe that, then we can always do the determinant of 0 minus 1, 2, minus 1, 0, 3, 2 minus 4, 2, and I will leave you to check that that's a 0. And there's another example in the notes that I won't go through where you can also do it with D, and then you can change the affine chart that you're working in, or just do the a calculation of the determinant. So let's go on to section 5.4, which is the cross ratio. So I think I will do that on a second recording.